So we'll talk about a few so-called multi-step methods. All right, methods. Right now, what we have so far is that you know un, you compute un plus 1, right? Un plus 1. That's one step. That's called one step. One step method. What if maybe we have un minus 1? I mean, when you have un, you have un minus 1 already. What if we compute something based on un minus 1 and un? We compute un plus 1, right? We compute un plus 1. Okay? That's called a two-step, right? Two-step method. Again, all these are coming from that original idea, that formulation, that integral formulation. So again, never forget about that, right? All the schemes are derived from there. What was it again? That's, you have the y prime is equal to ft(y). You get the initial condition y0, right? Y0, and what you do is that in general you have your yt, right? Yt is equal to y0. That means you start from 0 and you end with t. Okay, your y prime, which is your f ty dy, right? dt, right? Integrated with time. Or what in our case, the y tn plus 1 is equal to y at tn plus, if you go from tn to tn plus 1, you integrate from tn to tn plus 1, right? From tn to tn plus 1 of that f dt, right? Or, we start from 0, we start from tn, we certainly don't have to start from tn, right? Why not from tn minus 1? So this is like y of tn minus 1 plus, in that case, is from tn minus 1 to tn plus 1 of f dt. Right? As long as you see the connection with the integral, it's really everything is the same, right? In particular, this generates this little observation, right? Generates the so-called midpoint rule, midpoint method, a two-step method, which is, okay, our un plus 1 is equal to un minus 1. That's an approximation to the y at tn minus 1, right? That's un minus 1. Plus, we need to integrate from tn minus 1 to tn plus 1. Okay? And if we use the midpoint, which is f at tn, the midpoint of tn minus 1 to tn plus 1. Okay, it's the midpoint for that integral. So tn, and you replace yn by un, right? Times what? Delta t or 2 delta t? 2 delta t, right? 2 delta t. Again, this is integration. You think about the integration. Think about the integration. Here is tn minus 1. Here is tn plus 1 in the middle of tn. Right? This is to say, I'm going to take this guy. I'm going to take this guy. Right? This area. So think about it. Think of area and the integration, numerical integration. You take the height, the midpoint value, multiply by the width. Well, the width is 2 delta t, right? 2 delta t. Okay. Questions? We can also have a Simpson method, Simpson type, because we can do that integration. We can do this integration from Tn to Tn. This observation generates two methods, right? We can integrate from Tn minus 1 to Tn plus 1, that observation. In that case, our um plus 1 is equal to um minus 1 plus. Now, we integrate from Tn minus 1 to Tn plus 1, all right, by the Simpson's rule. We have Tn minus 1, and then Tn and Tn plus 1. What's the weight again? 1 over 6, 4 over 6, 1 over 6, right? So we are getting 6fm minus 1. By fm minus 1, I mean you plug in Tn minus 1, um minus 1, okay? I'm going to use a shortened name. And then you have 6, 4, fn plus 6 fn plus 1, right? Plus 1. And of course, we're not done yet. This should be multiplied with what? With what? So this is 2 delta t, which of course we can write it as um minus 1 plus delta t over 3, right? Cancel 2 with 6, you get fn minus 1 plus 4 fn plus fn plus 1. The first observation is that it's implicit. You need to solve for um plus 1, okay? The second is that say you have u0, okay? For this kind of two-step methods, you have u0. If I want to get to u1 by the formula, can we get to u1? We need n plus 1 to be 1, right? So n is 0. But we have n minus 1, so we need u negative 1. Or f I negative 1. U negative 1. We don't have, right? We don't have. So for the multi-step method, you have to start with something else to start. Maybe you use forward Euler. I get my u1, right? And then I have my u2. I can with u1 u0 u1 I get my u2. Okay, so u2 is like u0 plus 2 delta t times f1, or u0 plus delta t over 3 times f0 plus 4f1 plus f2, right? Again, for that case, you need to solve for u2. It's implicit. So this is to say that we use a forward Euler to start, which is usually necessary for multi-step methods, because in the beginning you only have one step, u0, right? So in general, you certainly don't have to start from Tm minus 1, right? If you think about it, we can start from Tm minus 2, Tm minus 3, right? Tm minus 3. So more steps? That's certainly possible. Say, you have your un plus 1 is equal to un minus 1 plus the integration from Tn minus p, right? Tn minus p to maybe Tn plus 1. Not maybe, it has to be Tn plus 1 because we wrote un plus 1. Un minus p is now, right? Un minus p corresponds to Tn minus p. You integrate from Tn minus p to Tn plus 1, okay? Of that f dt, okay? F dt. Then this becomes a p plus 1 step method, right? Step p plus 1. So let's work on, couple of examples. Of slightly different type again. So we're not going to do more of this type. The next is so-called Adams methods. Adams methods. Okay. So the idea is that we go back to the to the original setup, which is we integrate from Tn to Tn plus 1. Another approach, right? Over there is we start from something earlier and then we integrate from that point on. Here is that we only integrate from Tn. You have your f dt, all right, f dt, and we numerically integrate, as always is the case, integrate this Tn to Tn plus 1 of the f dt, all right, f dt, by extrapolating f. We talk about interpolation. We haven't really explained what is extrapolation, but we make it clear here, right? By extrapolation, f on, again, we go back to the Tn minus p, right? Tn minus p. Tn minus p plus 1 all the way to Tn. To Tn. By extrapolating f. Maybe I should change this. That is extrapolating f, comma. That is, we're going to no. So we knew numerically. So we extrapolate f, which means that is we interpolate. That is interpolating f on that interval and extending, all right, extending it to the interval Tn plus 1. So the keywords is what? Keywords are what? Extrapolating. Means that you interpolating and then extending. Those are keywords. Again, I'm going to show you two examples, right? So because we know the values of u before n, which give us the values of f before n, all right? So f is a function. What's the rationale? The f is a given function, but it's a given function of y, right? F is a function of t and y. We are integrating with, well, y is not known, y is unknown. So the function f is really unknown. But what's good is that we know f on those points. So you can interpolate, come up with a polynomial. Once you interpolate on the interval, you extend it outside. That's called extrapolation. It's a prediction. You come up with a model, you feed your data, and you predict what's later, right? What's coming later. That's extrapolation. Is that clear? That's all extrapolation means, okay? Okay. So another way is that this approach is called Adams-Bashforth. Adams-Bashforth. Or you just interpolating f maybe let's explain this later, okay? So to not confuse you. So let's do the Adams-Bashforth first, just A, B. Let's say, an example. Maybe a two-step. Maybe method. So what does that mean? That means, well, we need to compute un plus 1. We know that's un plus the integral for tn to tn plus 1 of that f dt, right? Of f dt. So two-step, we go back to tn minus 1, right? So we interpolate f on tn minus 1 tn. We know that value, right? We know that value. So f is t and y is function of t, so f is eventually a function of t. That's another conceptual delicacy, right? F is a total function of t. We know that, let's go slowly here. We know that when you give me tn minus 1, okay, we have that fn minus 1, which is what? If your f is 3y, for the example, then your f at tn minus 1 is 3 times the un minus 1, right? You know the value. We know f at tn is equal to fn, right? Again, ed is 3 times un minus 1 for f ty to be 3y, okay? This is what we're doing the interpolation, right? We interpolate. We go back to n minus p. P is 1. This gives you p plus 1 step. This p is 1, 2 step. Okay? We do the interpolation. All right? Of 2 points, how do we interpolate 2 points? So f of t is approximately equal to, by interpolation, right? Okay, 2 points we use degree 1, right? Degree 1. N plus 1 points degree n. 2 points determines a straight line, right? Straight line. What is a straight line? To write down a point slope form, right? Fn plus minus 1, or the Newton form, right? And the Newton form is what we are doing here. Slope is Fm minus 1 divided by delta t, that's the slope, times t minus 1, right? Okay. So what this is, schematically, is that you have Fn minus 1, Fn, all right, and the function of function of f is unknown. Maybe this is like your f, right? What you do is that you take these 2 points, you come up with a straight line. Here's Tn minus 1, here's Tn, next is Tn plus 1. Tn plus 1. We need to integrate. We need to integrate from Tn to Tn plus 1, right? So we're doing interpolation on Tn minus 1 to Tn, and then we extend the function. We extend this function over here and integrate that guy. That's all. That's all. With 2 points, we can write down a linear straight line, right? That's what we did. When t is equal to Tn minus 1, this is 0, you get Fn minus 1. When t is Tn minus 1 delta t. Delta t cancel delta t, you get Fn minus 1 plus Fn minus 1. You get Fn. So we satisfy these 2 points. Okay, and this is straight line. Extend means that we are integrating extend to Tn to Tn plus 1, which means we're integrating f on this interval, right? We don't really know what f is because we don't know f, we don't know y, we don't know the u on that interval. But we have a representation for f, the whole f already, which was good up to Tn. But we're going to, when delta t is small, it will not be too bad after that. We just extend it. Which means instead of doing something else, we integrate the f. We integrate this interpolated f. Right? So un plus 1 is equal to un plus from Tn to Tn plus 1 of this interpolation. Fn minus 1 plus Fn minus 1 divided by delta t, t minus Tn minus 1 dt. Okay. How do we integrate this? We're integrating this straight line, right? This straight line. So yes, instead of going back to the calculus, just do your trapezoid rule. Right? So what is that? That is delta t times a half of the first point plus last point. You don't need to do the t squared over 2. The first point, you plug in Tn, right? Which we know is you are going to get Fn. Because that's how the function is interpolated. Now you plug in Tn plus 1. Alright, so you're going to get your Fn minus 1 plus plus what? When your t is Tn plus 1, you get 2 delta t. Okay, so we're going to cancel that. You get 2 Fn plus 2 Fn minus 2 Fn minus 1, right? So this is nothing but un plus delta t times 3 over 2 Fn minus 1/2 Fn minus 1. Am I right? So 1 minus 2, yes. Fn, you get 3 copies. So this is a 2-step Adams-Bashforth. I want you to take a really good next is outline the next example, and I'm going to leave it as homework. All right. Is to go 3-step. So again, we start from this of f dt, right? F dt. Again, the first step is you interpolate. Okay, so now we have on Tm minus 2, you get Fn minus 2, right? And then on Tn minus 1, you get Fn minus 1. On Tn, you get Fn. Okay, we take one more step backward. So you interpolate f, all right, on Tn minus 2 to Tn by a what polynomial? A quadratic, right? A quadratic polynomial. A quadratic polynomial. Okay? And then you integrate. You extend it to Tn plus 1. You pretend that f on the new interval is that same function. Right? The same function. You integrate the interpolated f on the new interval, right? On the new interval from Tn to Tn plus 1. Which is, if we were to write it down, this is un e plus 1 is equal to un plus, we integrate from Tn to Tn plus 1. All right? Of a quadratic in the interpolation, which we can write it down because, say, we can do the Lagrange form, right? So we have Fn, okay? We get T minus Tn minus 1 times Tn minus 2 divided by divided by what? So we're doing the interpolation on these 3 points. Okay, these 3 points. So starting with this guy, Fn, t minus tn minus 1, t minus tn minus 2, divided by the characteristic polynomial for that point, right? So yes, you plug in the one you skip, which is 2 delta t squared, right? Plus the one is the fn minus 1 is then t minus tn times t minus tn minus 2. So I was using the lower one, which should be just as the upper one. Divided by, in this case, you plug in tn minus 1, you get a negative delta t times delta t, which is negative delta t squared, plus the last one is fn minus 2, right? T minus tn times t minus tn minus 1. And you plug in tn minus 2, you get a negative 2 delta t times negative delta t. Right? You get 2 delta t squared again. You integrate this function on tn to tn plus 1. Right? Then you will get, after you do the integration, you will get this un plus 1 is equal to un plus delta t times some number times fn plus another number times fn minus 1 plus another number times fn minus 2. Okay, because why? You know, fn minus 1, fn minus 1, fn minus 2, fn minus 2. The rest is polynomial. Once you integrate, they disappear. Okay, they disappear. And of course, there's a trick here as well. If you don't do if you don't go back to calculus and do t cubed over 3, we can use what to make this exact. This, I mean, I don't think this is, you know, as easy as that one, but it should be easier than doing all the quadratic integrations. If you actually multiply the amount, you get t squared minus a lot of stuff. And then you go to t cubed over 3, right? You need to evaluate tn plus 1 cubed minus tn cubed. That's a headache. If you use a rule, what rule?
I guess Simpson's or Woodson.
Yeah, Simpson's. Apply Simpson's rule to each of them. Then one great thing you can see is that you see they're just numbers. All the tn plus 1, tn minus 1, they all go away. Because you plug in if you do a Simpson's rule, it becomes evaluation at some points. All the delta t will cancel. You evaluate this at some point, you get some multiple delta t here, some multiple delta t there. You cancel with the denominator. So again, so just use Simpson's, right? To integrate.